Okay, guys, so let's start. Okay, so good afternoon, everybody. So last time I started chapter 2. Chapter 2 is also very small chapter. In this chapter, I started to discuss some circuit elements. So the first element here I discussed this. So here I told you whatever the element is, usually the relation between I and V depends on the element itself. So also here I told you we have voltage sources and current sources. Both of them are energy generators, so they generate electrical energy to the circuit. The main difference between them is actually here the voltage source, the voltage should be constant, okay, but the current changes based on the rest of the circuit, okay? So by changing the resistance, so ideally, if you have a battery, this battery is 5 volt, okay? So it should be 5 volt all the time, should be. The voltage across the battery should be 5 volt all the time. But by changing the resistance that's connected to the battery, the current may change, okay? The current will be different, okay? For the current source, the current is constant, so it's going to give you the same current all the time, but the voltage across this source depends on the resistance you are connected. Okay, so if I connect a resistance here, so this current, for example, is 1 ampere, so this one is going to continue, is going to be almost 1 ampere regardless of the resistance you are connecting here. Okay, but the voltage is going to change based on the resistance you connect here, okay? So that's what I explained last time. Also, I explained we have, for example, this one is constant voltage source. It means the relation between the voltage and the time is constant. It does not change with time, okay? But this one time varying. So this one can be like a sine wave, can be any other wave, but it depends on the time, okay? Also, I told you we have two types of sources. One is dependent and one is independent. So you can tell from the English name. So independent, that means the amount of voltage here, the amount of current here, the amount of voltage here does not depend on the rest of the circuit. Okay, if it's 5 volt, it's going to be 5 volt. Okay. However, here, and you need to be familiar with the symbols. Okay. So here, if we use the symbol diamond, as you see here, so that means this one is dependent current source. So dependent means the amount of voltage here depends on a certain element in the circuit. Okay. Same thing here. This is a current source, but this current source equal to G. G is constant. V node. V node is actually a voltage in the circuit. That means if you change the voltage, you are going to change the amount of current here, okay? But still, if you don't change it, if you don't change V node, the amount of current here is going to be constant all the time. The voltage across it is going to change because this is a current source, okay? So actually, these dependent sources are usually, we're going to use them to model something like transistor. So if you have a transistor like this one, in order to model, so what do you mean by model? Model means I want to find a circuit like this one, so that this circuit is going to act, is going to behave similar to this transistor. Okay, so this transistor should behave this way. The current here is proportional to the voltage here. Okay, so that's why I can say we have a current source here. This current is constant. If as long as the voltage is constant, the current is constant. Okay, that's why. But the amount of current is proportional to VBE, the voltage here. So that's why I'm gonna model the behavior of this transistor is something like that. This is the base, which is P here. This is the collectors, like this one. This is E, which like this one. And then, and here we have a current source, okay? But this current source is dependent because the value of the current here depends on the amount of voltage you have, okay? But again, I don't want to be confused. This one is still current source. Current source means the amount of current is does not change when you connect a resistor here, okay? It does not change. But what it changes is the voltage across it, because this is a current similar to any current source, okay? The only difference between dependent and independent is the amount of the current here is actually proportional to a certain part of the circuit. So if you don't change VBE, so the current here is constant, okay? And then by changing the resistance, the voltage it changes, okay? Anyway, that's what I explained last time. Also, very important to understand the concept of a node, what node means, okay? Because we're going to use it all the time. Node means connection. When you connect, for example, here, all of this is one point or one node, one point or one node. Oh, and for a node, so it has the same voltage everywhere. So the voltage here is similar, because this is like a copper wire. It has, we assume it has zero resistance wire, okay? That's why the voltage here similar to the voltage here, similar to the same voltage, okay? Same thing here. All of this just 1 point, okay? This is 1 point, okay? All of this 1 point. Okay? So that's the definition of a node. And then you need also to know what I mean by ground node. Ground is one node. I'm gonna consider the voltage of this one is 0. Okay? And actually, this would be my reference point. My reference point. That means any voltage, if I calculate the voltage here, and I say the voltage here is 7, as I told you, nothing is, I say this point has a voltage 7. Usually, voltage means difference between 2 points. Right? You got what I'm saying? That's true. So when I say the voltage here is 7, that means the voltage difference between this one and the reference here is 7. Okay. I think I give you this example last time, and yeah. So here in this example, as I told you before, power is actually V times I. Okay, and power either it is consumed by some elements or generated by some elements, and the total of generated power should equal to the total of consumed power. Okay, makes sense? So here you have this source and you have this source. These two sources are generating power. And for sure, I don't know what are these sources because it didn't tell me. But for example, if you assume they are resistors, so these elements actually are consuming power. So some element generating, some element are consuming, and the summation of received should or generated should consumed should equal to summation of generated power, okay? And power is just V times I, okay? Also, last time I started to explain or I explained resistance, okay? You can take from the English name resistance, you resist, okay? So this material is resisting the current, okay? The current cannot flow easily because of it's receiving a resistance. Anyway, and I told you the resistance, it is measured in ohms, and one over the resistance is called conductance, or we call it G or conductance. You can tell again from the English, higher resistance, that means you receive, that means too much resistance to the current. Here, conductance, so the smaller, this number can tell you is one over the resistance. Okay, so this one can tell you how good in this conductor is. So as this value increases, that means this can deliver or electricity better. Okay. Anyway, so, and I told you it's related to the material itself. And then I explained Ohm's law for resistance. Ohm's law gives you the relation between V and I, V across. V here means the voltage drop. And be careful, when I say this is positive and this is negative, it doesn't mean the voltage here is actually positive and the voltage here is negative. It doesn't mean that. Maybe this one 10 volts, okay, and this one, for example, 7 volts, for example. But it means the voltage here, the volt here is greater than the voltage. That's why current is flowing from the high voltage to the small voltage. So anyway, I got the relation V equal IR, okay? And then using this one, I was able to get a formula, a new formula for the power. So B equal VI, this is a general formula for any element, but for resistance, because I have a relation between V and I, so I can say power equal I square R or V square divided by R. Be careful, these two formulas are only used for resistors, okay? But this one is a general formula. Okay? Anyway, and finally also, I think last time I explained what is short circuit and what is open circuit. So open circuit means it's like you have infinity resistance. When I say the resistance infinity, okay, it's open circuit, because if the circuit is open this way, the current cannot flow here. There is no current, so the current here is zero. No current can flow if it is open circuit, okay? Short circuit, that means, okay, it's gonna be the same voltage. It's gonna be all of this, like the current here is gonna be the same current flow this way. It's gonna be the voltage drop here is zero because it's the same voltage. The voltage here is similar to all of them just the same voltage. So if you want to get the voltage drop, the difference between this point and this point is zero because it's the same voltage. Okay. I think I explained also this one last time. So and also I started to explain how can we model a battery. So here. So if the battery is ideal battery, okay, so it has to be this way. For example, this is the battery, and then I have here a resistance RL, and then I connect it this way. Okay, so this one is 5 volts, so it's gonna be here 5 volts, regardless of what is the value of RL. So when you change RL, still the voltage here is 5 volts. In reality, it is not like that. In reality, because the current inside the battery itself is receiving some resistance, right? So in reality, the battery should be something like that. This is the ideal one, and then we have a small resistance here, and this is the battery. So when we model the battery, you have to take into account that there is a series resistance this way, and then we have here RL. Okay, so because of this one here, there is a voltage drop here. So if this one is 5 volts, I'm not gonna receive here 5 volts because there is a drop here. Okay, if the drop here is, for example, is 1 volt, so here is gonna be 4 volts. Okay, from here to here is gonna be 4 volts. If this one is 2 volts, so I'm gonna receive 3 volts. But usually this resistance, it's a small resistance. If this RL is big resistance, sometimes we ignore this one, but you need to understand practically there should be some resistance here. That's why and this can result in having a voltage here on the battery that is not exactly 5 volt, but maybe a little bit less than 5 volt. Okay, so if you can see here, what is the current here? The current, so I should equal 5 volt divided by the two resistors, RS plus RL. This is the current flow here. And by this way, you can say the voltage here, VL, the voltage you are going to receive, should be VS, which is this one is VS, the 5 volt here, minus IRS, the drop on this one, IRS. Okay. By the way, the same thing for if you have a current source, it's the same thing. Okay, but the resistance here is not series. Instead of it is parallel. So it's, you have a resistance this way, okay? This is ideally we don't have this resistance, but in reality you have this resistance, and this resistance usually it is very high. So that's why most of the current here is going to go this path, because this path usually has very high resistance. Here, this resistance is a small resistance. Usually, it's a small resistance. That's why there is a small voltage drop here, and most of the 5 voltage should be here. Okay. Yeah, so that's what I'm explaining here. We have a small resistance here, Rs. Okay. And then I calculated VL, the voltage drop here. I calculated this way. The voltage drop here is actually VA minus VB this way. And I'm gonna add C, VC, and subtract C. Okay, so if you do this way, so the first part here, VC minus VB, VC minus VB, which is VS. Okay, and the second part here is VC minus VA, VC minus VA, which is the drop, voltage drop across this one, which is actually according to Ohm's law I, the current I times Rs, this way. So that means the voltage I'm going to receive here is ideally it has to be Vs. In reality, it's going to be Vs minus the voltage drop across this one. Any questions? Again, usually if this resistance is high resistance, okay, so usually this one you can consider it like a short circuit. So if you have high resistance and then in series with a small resistance, usually we can ignore this one, and actually most of the voltage will be here. Okay. Anyway, any questions? Okay. So now I'm gonna talk about. So I already explained some basic elements in electrical circuits. Now I'm gonna talk about ammeter and voltmeter. So ammeter and voltmeter, these are used for measurement. If you want to measure current, if you want to measure voltage. So I'm gonna explain how, number one, how we connect them. So let me show you. Yeah. So this is the picture. So you know this measurement device, okay? So ammeter is used to if you want to measure the current. Voltmeter is used if you want to measure the voltage. So the first thing I want to talk about is how we connect them. Also, ideally, how they should behave. Okay? So look here, guys. For example, I have here a battery. I have a resistance here. And then, for example, I have another resistance here, assuming we have something like that, okay? I want to measure the current flow this way. So I want to measure this current, okay? So the way you have to do it, guys, is you have to open, you have to cut, you have to open this one here. You have to open it, okay? And then you have to connect here the ammeter. So the ammeter has to be connected in series. That means the current I want to measure, so this is ammeter. So the current I want to measure has to flow, it has to flow through the ammeter. Is that okay? So if you want to measure the current, you have to open the circuit, you have to connect the ammeter this way, so that the current you want to measure, it has to flow through the ammeter. Is that okay? Ideally, this ammeter should have a resistance of 0. Ideally, the resistance of this one should be 0. Okay? In reality, it has some resistance. What is the problem if this one has some resistance? Can anyone think about it? If this ammeter, for example, has some resistance, like for example 20 ohms or something like that, what's the problem? I told you ideally it should be 0. Okay? In reality, it's not 0. There's a small resistance. What this resistance can make?
Voltage drop.
So, sorry?
A voltage drop.
Yes, it's going to make a voltage drop, but what is the problem with the voltage drop?
Lose power in circuit.
Splitting the current between two different branches.
It's not in parallel, okay? It's a series, so it's gonna be the same current this way. Okay, I'm gonna tell you what's the problem here. You're very close, but I'm gonna tell you what is the problem here is simply you change the circuit. You added a resistance to the circuit, so the current is gonna change. So if this one is a short circuit, let me give you example. For example, this one is 1K and this is 1K, for example, and this is 5 volt. So the correct current I have to measure is actually 5 volt divided by 1 plus 1, 2K. This is the correct current. However, because you added, you changed the circuit, you added a resistance to the circuit, you disrupted the circuit. Because of this resistance, current is gonna change. You got what I'm saying? So it's gonna be plus RA, for example. RA is the ammeter resistance. So that means it's gonna be source of error. So the higher this RA is gonna be, you are not gonna measure the exact current because you added a resistance by using this device to the circuit. That's why ideally, this resistance has to be very small. Any questions? So number one, guys, what I'm explaining here, number one, we have a device which we use, it's called ammeter. This ammeter is used to measure the current flowing in any branch, in any circuit. Number two, you have to connect this one in series. So you have to open, yeah, for example, if you have here something like that. If I want to measure the current flowing here, okay, so I can put it here, the ammeter, or you can put it here, it doesn't matter because it's the same current. What's really important is that this current has to flow. And I have to open it, so it has to be in series. So I have to open it this way, so that the current here is gonna go through the ammeter. Is that okay? If I put it here or you put it here, it's the same, okay? Because it's the same current. If I wanna measure the current to flow in this branch this way, I can put it here, I can put it here, I can put it here, because you can see it's the same current. What's important is the current I wanna measure, it has to flow through the ammeter. Any question? So number one, you need to know how we connect the ammeter, why we are using it to measure the current. Number three, what kind of error this ammeter can cause if it has resistance. Okay, any questions? Now I'm going to move to the second device, voltmeter. Voltmeter is used if you want to measure the voltage, okay, across an element. For example, if you have here, so if you have a circuit like this one, and I want to measure the voltage drop here, I want to get V. I want to measure the voltage here. Is that okay? Number one, as long as you want to measure the voltage, so I have to use voltmeter. That's true. So number one, how we connect it, the way we connect it, okay? The way we connect it, it has to be connected in parallel. So I have to connect it. So you don't need to open the circuit. You don't need to open the circuit. You connect it in parallel. Is that okay? So that the voltage here has to be the same voltage here. Okay. This is the way you have to connect it in parallel. Also, ideally, the resistance here has to be infinity. It has to be very high resistance, infinity. It's different from what I explained here. Here, this one is connected in series, so you have to open the circuit this way. You have to open the circuit and you have to connect it this way. And ideally, it has to act like a short circuit. Ideally, usually it has a small resistance that can make some error in the measurement. Here, it has to be connected in parallel on the voltage drop I want to measure. So if I want to measure here, so I have to connect it here in parallel. I have to connect here in parallel this way. Okay. Same thing if I want to measure it here, so I have to connect it in parallel this way. Okay. Ideally, the resistance here has to be infinity. Practically, it's not infinity. There is some resistance here. What is the problem because of this resistance? What this resistance can make? Similar to what I explained the other one, so in the ammeter. So what's the problem if you have here a resistance that's not infinity? What's going to happen? Yeah, you added a resistance to the circuit. You got what I'm saying? By adding a new resistance to the circuit, the voltage you are going to measure is not going to be the same voltage. Okay? In other words, we have a current here, and I'm gonna call it I. What I have to measure is actually I times R. This is R, the resistance here, I'm gonna call it R. So the voltage drop I have to measure is actually I times R. Assuming this current is gonna flow, all the current is gonna flow this way. Is that okay? In reality, what happens, because you added a new resistance, not all the current is gonna flow this way, but there is some current to flow this way. I'm gonna call it, for example, IV, I voltmeter, okay? So although I have to measure I times R, what I'm gonna measure is actually, so here, the current, so the current here is I, so here what's gonna flow this way because of the disruption happened by the voltmeter is actually I minus IV. So the current is gonna split. So this current is gonna split between these two branches. So what I'm gonna measure actually is I minus IV times R. This is what I'm gonna measure. So this will be source of error. Okay. So ideally, the voltmeter should have infinity resistance, or so that most of the current has to flow this way. Okay, guys. And you can learn something related to this one, related to circuit, very important. Listen to me. If you have related to exactly what I'm explaining here, if you have a resistance this way and you have a resistance this way, normally, as I'm going to explain, if you have a current here I, this current should split here, for example, I1 and the I2. Because keep in mind, I means charges. These charges are not going to go anywhere. So if you have here a certain amount of charges, should equal to the summation of the charges in these two branches, right? Because the current is not going to go anywhere, it's not going to fly. You understand what I'm saying? So the same charges here is going to split this way. Yeah, that's true. And then here I'm going to get I again. Because it's the same charges are going to come here, okay? So, the point here is that, listen to me. For example, here you have R1 and you have R2, okay? So, if R1 equal R2, if they are equal, so this current is gonna split equally, okay? But if one of them, as I increase one, for example, I'm gonna increase this one, I will see more current is gonna flow here. If I make this one very, very high, so all the current is gonna go this way. So usually if you have two resistors in parallel this way, more current is gonna flow in the branch that has small resistance. You understand what I'm saying? That's why, for example, I can have here, for example, 2 ohm resistance. If I connect here multiple resistors, every one, for example, 1K, 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 actually you can put, it's okay to assume all the current is gonna go this way, and 1K for 2 ohms is actually infinity. So infinity does not need to be infinity. You get what I'm saying? If you have a very big resistance and small one, almost 99% of the current is gonna flow this way. Yes, 1% is gonna go this way. So maybe the error is gonna be small error, it should be okay. Anyway, so I'm just explaining it because it's somehow related to what I'm explaining here. What I'm explaining here, number one, if you wanna, voltmeter is used to measure the voltage across elements. You have to connect it in parallel. Okay, this is number one. Number two, because ideally this resistance should have a very high cut, very high resistance. This voltmeter should have very high resistance. Actually, most of the current is going to go this way, 99%. There is a source of error. Yes, there is a source of error, but if this error is very small, it should be okay. If ideally, if this one is infinity and all the current is going this way, so that means you didn't make any disruption to the circuit. Any questions? You understand the idea how a meter or a voltmeter can make disruption, and this can cause, or this can make error in the circuit. Okay. So anyway, so here you may be familiar with some of these devices. I think now most of the people, no one is using the analog devices anymore. I think so. Most of the people now using the digital ones. Okay. So for example, here the last slide here in this chapter is a very simple one. Just I just wanna ask you, or you need to know how you connect, okay? Because the way you connect the voltmeter or ammeter is different. So for example, here this is the circuit we have. If I wanna measure this current, So you need to open, I need to open this circuit so that this current has to flow through the ammeter. And that's what I did here. Look, I have to open it this way. So that the current I want to measure, it has to flow through the ammeter this way. Okay? But in case of voltmeter, no. Voltmeter, we connect it in parallel. So if I wanna measure the voltage from here to here, so I'm gonna connect it this way. And again, if these devices are good devices, this one should become like open circuit, infinity resist open circuit. Otherwise, it's gonna be disruption. This one should be, because it is series, it has to be like a short circuit. Okay, so that it does not disrupt the circuit. It does not have impact on the current or the voltage. Any questions? Okay, good. So in chapter 2, I'll just explain some elements, some circuit elements. In chapter 3, I'm gonna start teaching resistive circuits. So the resistive circuit, these are the circuits that mainly has voltage or current sources in addition to resistance. Okay, so here what we are gonna do here, there are three main laws. You need to know these laws here, okay? Because that's what we are gonna teach in details in this one. So in this chapter. So there are three main laws that govern all electric circuits. The first one here is Ohm's law. I already explained Ohm's law. The voltage drop across any resistance, voltage only for resistors, should equal I times R. Okay, this is the voltage drop. Okay? Second, I'm going to teach Kirchhoff current law, and then Kirchhoff voltage law. TCL and TVL. So very important. They are very basic, laws in circuits. Very important for sure. So let's. I'm gonna start teaching it here. But again, the purpose of this slide, I want you to understand what I mean by the word node. Maybe I explained it multiple times what node means. I don't want to be confused because we're going to use it all the time. Node. Okay. So for example, if I connect a circuit this way, so this is a node. So here, this element, this are connected together. That's why this is a node, as you see here. Okay. So this one I can draw this way. So this one and this one are identical. There is no from electrical electricity point of view or electrical circuit, these two are identical. There is no difference because this is like a wire. This wire has zero resistance. Okay, so if you make it small like this one, if you make it long, it's not going to make any difference because just a short circuit. Okay. Anyway, so so this is all of this just one node. Yeah, one node here. Okay, hopefully you are not. This is also one node. Okay, so any points that connect these two devices together. So this is one node here, as you see. Okay, this is another node here. So we have node A. All of this one node. This is one node, one node, one node. Okay, every node has the same voltage. So if the voltage here is 5, here is 5, here is 5, here is 5, here is 5. Okay, guys. Okay. So you will see, so all the time when we analyze the circuit, number one, you have to find the nodes, and then you work with these nodes. Anyway, so let's start with the first one, Kirchhoff current law, okay? KCL, Kirchhoff current law, okay? It's very, by intuition, look what this law is telling us. Okay, number one, for any node, the amount of current entering this node is equal to the amount of current out of this node. So for any node, the amount of current input should equal to the amount of current out of this node. Does it make sense? For sure makes sense because current means charges. Okay, so the amount of charges enter a node should equal to the amount of charges are going to get out of the node. They are not going to fly in the air. You understand what I'm saying? So there are certain amount of charges input to a node. So the same charges has to get out of this node. Okay. So this is Kirchhoff's current law. For any node, summation of the current in should equal to the summation of the current output. Okay. For example, look at this example here. This is a node. This is a node because we connect multiple elements through this node. This current is input to the node I3. This current is output. This current is input. So based on Kirchhoff current law, input is I1 plus I3. I1 plus I3 should equal to I2 out. Is that okay? So this one can give us a, okay, guys. So as you will see, guys, when we analyze a circuit, we have to make a number of equations, and then we solve this equation. So this is one of the way to make equation to get the relation between the currents in the circuit. Okay. So if you look at this one here, for example, this current is input, this current is input, and this current is input. Okay. Nothing is out. For sure, it doesn't make sense, but for sure. Okay. But that's okay. You can assume that, no problem at all. You can assume that. But after you do the calculations, you will find some currents are negative. You get what I'm saying? So yes, that doesn't make sense that if everyone is input. Okay. So here, yeah, if you that's okay. You can assume this way, no problem at all. And then your equation will be I1 input plus I2 input plus I3 input should equal to 0. And then you can continue the calculation because I'm assuming this is the direction of current, but I'm sure 100% after you do the calculation, some of this current will be negative. Negative means it has to be out, not in. You got what I'm saying? That's why I told you can assume the direction of current in any direction, and then after you do the calculation, if it is positive, that means the direction is correct. If it is negative, that has to be the other direction. Okay? So let's look at this one here. Okay. Also here, here this one is out, this one is out, this one is out. So there's no input. That's okay. It may happen to see something like that, but I'm sure after you do the calculation, there should be some current input. So the input should equal to the output because this node is not gonna generate charges. Okay? No, the charges are coming from the sources and then they are distributed. That's why there should be something, or after you do the calculation, then again, this is okay. You can, if you assume the direction this way, it's okay. But after you do the calculation, it should make more sense. Okay. So here, because this one out, there is no input, so out should equal to input, which is 0. Okay, guys. Again, as you will see, when we analyze the circuit, we need to find the relations between voltage and current, and then using these relations, we are going to make equations, solve the equation, and then you can get the current and the voltage everywhere in the circuit. This is the main idea. So this one should help me to find some relation between currents. So I give you here a lot of examples. Look here, guys. This is a node. In this node, I have input current coming this way. This current is 10 ampere. I have current out 5 ampere, and this one out, I don't know how much is this one. Okay, so here I'm asking you to calculate this one. This is, you can just direct implementation. This is just a direct implementation of Kirchhoff current law. Okay, so here summation of N equal to summation of I out. So which one is N? This is N, and these two are out. Okay, so here I3 should equal I2 plus I1. Is that okay? And so 10, this one, so here this one is given, this one is given. We have only one unknown, so I can calculate it. So this one is 5. Because this one is 5. So what happened here is 10 ampere came this way, and 5 is gonna go this way, another 5 is gonna go this way. I'm not gonna lose current because current means the charges. The charges are not gonna fly. Okay, so the amount of charges or the amount of current in time should equal to the total of current out. Okay, we have another example here. I'm gonna assume we are given to us the current here entering. This is a node. This node is connecting multiple elements together. The current here is 2. There is a current here input here. I don't know what is the amount of this current. This is what I want to calculate. there is a current coming from a current source. This is a current source, this is a voltage source, and then current getting out here is 5 ampere. Okay. So again, I'm assuming the direction this way. Okay. So actually, this one is given to me, this one is given to me, this one is given to me, this one is not given to me. So I don't know. I'm gonna assume it is this way. Okay. So let's again, this is just the current input. So this one is input, this one is input, and this one output, and this one is output. So input here 2 plus 6. Okay. 2 plus 6 plus I is equal to 5. And then after I did the calculation, I found this one negative. So what it means it is negative. So actually this one should be out, not in. Now it makes no sense. Okay. So this one, so if you see here, two input, 6 input, total 8. Total 8. 5 here and 3 here. Now makes no sense. Is that okay? Any question here? This one should be easy, right? This is one of the very basic, the very important laws that we are using all the time. So it's based on the conservation of electric charges. Okay. Any questions? Again, there are 3 important laws we are using all the time: Kirchhoff current law, Ohm's law, and also Kirchhoff voltage law. So I'm gonna come to this one, voltage law. Okay. So Kirchhoff voltage law, this one is based on conservation of energy. Conservation of energy. You got what I'm saying? So remember, voltage is actually the amount of energy that is used to move from one point to another. Okay. So for example, here, if you have a very small circuit like this one, okay, so the voltage here should equal to the voltage here, because I'm not gonna lose, we're not gonna lose energy. Or the difference between these 2 voltages should be 0, as you have here. So here in Kirchhoff voltage law, as you will see right now, I'm telling you for any loop. So I'm gonna tell you what I mean by loop. So for any loop in the circuit, for any loop, the summation of the voltage should equal to 0 for any loop. So the summation of all voltages in any loop should equal to 0 at any time. So what do you mean by a loop? A loop is any closed path through a circuit, okay, that does not have an intermediate node. For example, I'm going to give you more examples now. So for example, here, this one can be a loop. So this one is a loop, where this one can be a loop. Okay, this one is a loop, this one. Okay. So here in any loop, so let me look here, guys. For example, here, for example, I have 5 volts. Okay, and then we have a drop here of 3 volts, and then I have drop here of 2 volts. Is that okay? And this one is positive, this one is negative, so the current is flowing this way. This one is positive, this one is negative, so the current is flowing this way. Is that okay? So actually, the way it has to be is, for example, if you take this loop, so actually this voltage here, which is 5, this voltage which is 5 should equal to the summation of the other 2 voltages, should equal 3 plus 2. Okay? In other words, if I move this one to the other side, the summation equal to 0. So it's 3 plus 2 plus 5 is, sorry, minus 5 is equal to 0. So you can see it this way, or if you can move this one, the summation is equal to 0. That's why the way we are going to do it is, look here. This is a loop. This what we are going to assume you have current this way and you have the current this way, and then we are going to assume a certain direction for the loop. It can be clockwise or counterclockwise. It's not going to make a difference. I'm going to assume it is this way. Okay. Look here. How we apply Kirchhoff voltage law. Okay. How we apply it. Okay. Again, this one is coming from the energy conservation law. So the amount if energy here should act generated equal to the amount of energy. Anyway, so the way we do it is here, because the direction of the current is similar to the same direction like this one, similar to this direction, this one. So I'm gonna take them positive. So here I'm gonna be positive 3 plus 2. So I'm gonna take this one positive and this one positive. Why? Because the direction, this direction is the same like the direction of the current here. If it is not the same, if something like that, I would make this one negative. Okay? So again, make it easy. For the resistors, if the direction of the current is the same like the direction of the loop, the current of the loop this way, if it's the same, so I'm gonna take the drop here positive. If it is opposite way, I'm gonna take it negative. So from now, let's take this case, for example, here. So here I'm gonna say 3 plus 2, because it is the same this two, okay? So, and for the resistors, for the voltage source, look how it works here. Is actually, if you input from the negative side, like this case here, the direction here, the direction into the current is from the negative side, so you have to make it negative, equal to 0. If the current here, if you assume it is this direction here, and it is input from the positive side, you have to make it positive. Okay, so here, if I want to apply Kirchhoff voltage law. So here I'm going to make it this way. Okay, so I'm going to say this is 3 positive plus 2 positive. Okay, minus 5. Why minus 5? Because this one is input here to the negative side, should equal to 0. Okay, so actually it has to be this way, but it has to be, because you know the current is flowing this way, right? The current is flowing this way. So actually it has to be 3 plus 2 should equal to 5. Okay? Because current here is the same direction like this one, current here is the same direction like this one, current here is the same direction like this one. Okay? But because I'm gonna move this one to here, so that's what I'm saying. If the current is input from the negative first, so this one has to be negative, because it's like you moved it this time. Okay, so if you are confused about the polarity, look what I'm gonna do right now here, guys. Look. Okay. Again, all what I said here now is I'm gonna take the direction this way. Okay. So here I'm gonna say 3 plus 2 is 3 plus 2 minus 5 is equal to 0. Okay. That's okay, because this one is input from the negative side. What if someone wanna take it in opposite way, this way? Okay, it's the same equation. Look here, but here, because the direction here is different from this one, should be negative 3 minus 2 plus 5 is equal to 0. So I got the same equation. Okay, so again, make it simple. Number one, for every loop, you need to assume the direction in a certain way, and then if the current here is the same direction, I'm gonna get the voltage drop here positive. If the direction is different, I'm gonna take it negative. For the battery, this is for resistors. For the battery, if you input from if the direction here is encountering, if it is encounters the positive first, like this case here, encounter is input from the positive. Okay, so take this one positive. If it is this way from the negative, take it negative, and then add everything together, you will get 0. Okay. Anyway, the best way to understand it by examples, and you have many examples here. I'm gonna teach right now. Okay. So let's see now. So now, guys, let me summarize what we did so far. What before we have many examples here, because the best way actually to understand this one is using example. So let me summarize the 3 main laws that we're gonna use all the time. Okay. Number one, we have Ohm's law. Ohm's law is very easy. If you have a resistance, if you have a current this way, positive, negative, you have current this way, so the voltage across, so V, it should equal I times R, I here, times R. This gives you the voltage drop. And again, drop means the voltage here, V1 minus V2, voltage drop, V1 minus V2. Because the current is gonna, current always flows from the high voltage to the small voltage. Okay? This is Ohm's law. Number two, we have Kirchhoff current law, very simple. For any node, the amount of current input should equal to the amount of current output for any node in the circuit. Okay, so now I can get a relation between the different current here. So I have I1, I2, and I3. So in this case, we have two inputs, so I1 plus I2 should equal to I3. Number three, Kirchhoff voltage law. So here, for example, you have a branch this way, for any loop, this way, okay, summation of the voltage should equal to 0. But you need to be careful about the polarity. You need to be careful about the polarity, okay? If the current is flowing this way and it has the same polarity, the same direction of you are assuming here, it's similar to the current this way, so I'm gonna get the voltage drop here. For example, I'm gonna call it V1, V2, and Vs. Okay, so because it's the same direction, I'm gonna get it positive. V1 plus V2 should equal, minus Vs equal to 0. Because this one, for resistance, if it is in the same direction of the current, okay, so it's gonna be positive. If it is in a different direction, so I'm gonna take it negative. For the battery, if it is input from the negative, I'm going to take it negative. If it is input from to the positive, I'm going to take it positive. Okay. So let's have several examples, because again, the best way to understand this part is examples. Okay. Let's start with this example here. I give you this circuit, as you see here. We have a voltage source here. We have a resistance here. We have a resistance here. We have a current source this way, and then we have resistance this way. Okay. So now I give you some information, and then I ask you to calculate. Again, you need to understand what is the purpose if I want to analyze the circuit. So what it means, analyze the circuit? It means I want to find all the currents everywhere in the circuit. Also, I want to find all voltages. This is the meaning of analyze the circuit. So here I give you some information, and then we're going to get everything we don't have. So here I give you V1. V1 means the voltage across. I give you the voltage across this one here is 6 volt. Then I give you I3. I give you the current here. Okay. I give you R1. I give you this R1. I give you R2. I give you R3. Now I want to get everything else. I want to get this. I1 is given to me. No. So I need to get I1. Okay. Voltage here is given to me. No. This voltage is not given to you. So I want to get it. So I want to get the voltage across all elements and also the current across all elements. Okay? So let's start with again, try to think again, very simple. Number one, you need to see what information you have. Number two, we are going to use the three main laws, and we are going to use the equation we have to calculate everything else. Okay. So for example, I have something here very easy. So for example, if you look at if you see V3 here, V3, I give you the resistance, I give you the current. Can you calculate the voltage here V3? Yeah, this is a very straightforward. Ohm's law. So I'm going to use Ohm's law to calculate V3. This is very straightforward. So V3 should equal R3 times I3. I give you R, I give you I, I give you R. So by this way you can easily calculate the voltage drop. So the voltage drop here between VA, voltage drop VA to the ground is 4 volt. Okay. V3 from here to, okay. So from here to here, it is 4 volt. It's the same point. So the difference between A and ground is 4 volt. So here also the voltage drop across this current source also is 4 volt, because the voltage here, guys, is the same, because this is one node. A voltage here is the same like here, like here. That's just one, like here, it's just one node. Okay. So by calculating the voltage drop here, I can know the voltage drop across this element. Also, I can know the voltage drop here as well, because A here, it's the same point. A is like this one, same thing. This one, like this one, like this one. You understand what I'm saying? So now I got the voltage V3 should equal to V2, the voltage across this one, because all of this just one point. Okay. So if you look at this one here, what information do you have? I have R2. I have the V2, the voltage drop, which is equal to this one is 4, and now I need to get I2. Very simple. It's Ohm's law. So that's what I did here. So here, if you look at this element here, R2 is given to me. I was able to calculate V2, which is equal to V3. Now I can get I2 easily. I calculated I2. Is that okay? Now, if you look R1 here, R1, what information we have here for R1? This is very easy. So for R1 here, I give you the resistance and I give you the voltage drop. Also, you easily can get R, right? So if I give you the resistance, I give you the voltage drop, you can get R, right? Ohm's law, and that's what I did here as well. So by this way, I was able to get. I have the current I1. Okay, I have I1 here. I calculated it here by the voltage drop across divided by the resistance. Okay, so I was able to calculate this one. I2 here, I was able to calculate it, I2, okay. I3, I think I3 is given to me, okay. So what else you need to find? I told you, analyze means I need to find all voltages and all current. So if you look at this one, I was able to get the voltage and the current. This one, I was able to get the voltage, but I don't know the current yet. So I need to find this current. This one, I have the voltage and the current. This one, I have the voltage and the current. This one, I have the current because this current is similar to this current here, but I don't know the voltage. So I need to calculate the voltage here and also the voltage here. Let's start with this one. How I can get this current? Okay, this is Kirchhoff current law. Because if you look at this node here, look at this is 1.1 node. This current input, this current output, this one is input, and this one is output. Okay, so I have 3 output and 1 input. And I already know this current here, so it's easy to calculate this one. And that's exactly what I did in next slide. So what I did here in next slide, so here I'm gonna apply Kirchhoff current law in order to get this current here. Okay, so after I calculated here this current, I1, so here input should equal to the output. So this is input to the node, this is one node. This is also input, and these are output. So I have this one, I have this one, this one. I can get this current, and I got it by -3 ampere. So -3 means it should be in the other direction. It's not in this direction. So what is left here? The only one thing is left is this voltage. How can we get this voltage? We're gonna apply Kirchhoff current law. So we're gonna look here. I'm gonna assume the loop is this way. The loop is this way. Is that okay? So if you look here, the current is this way. So it's the same way of the loop. Okay. So I'm gonna take this one positive. So I'm gonna say V1 positive. Okay. Here the current also in the same way. So I'm gonna assume the loop is this way here. Okay. So it is in the same direction like I2. That's why I'm gonna take the voltage across this one positive, as you see here. Okay. And because the loop is this way here, and it's gonna input or it's gonna encounter the negative first, so I'm gonna make this one negative this way. Okay. As I told you guys, if you make the direction different, so here I'm assuming the direction is clockwise. So if you make it counterclockwise, you are gonna get the same equation, but what's gonna happen? This one will be negative, and this one positive. So it's gonna be the same equation. That's what we need to think of. Okay. Anyway, so after from Kirchhoff voltage law, so here I know V2, I know V1 easily. I can get Vs. I find Vs here. The voltage here is 10. We're gonna have one more. Okay. Let's have 1 or 2 more examples here. That's very easy examples. So for example, if you look at this example here I give you have 2 sources here, okay? You have 2 sources. This source is independent, it's 9 volt. This one is dependent, and this one is 3 Vx. And Vx is the voltage across this one, okay? So let's apply Kirchhoff voltage law to get relation. So make it simple. Ohm's law gives you a relation between current and voltage on one element. Current law, Kirchhoff current law gives you relation between current in one node. Voltage law is going to give you relation between voltages in one loop. Okay? So that's what I'm going to apply now. So here, don't think about it. Here, Kirchhoff current law is not going to help me because it's just the same current. Current here is similar to this one. It's just one current. Okay. But anyway, so let's apply voltage current voltage law. So I'm going to assume the loop is this way. Okay. So here this is positive, this is negative. So it is in the same direction of this one. Okay. So this one should be positive. Okay. Here you input from the positive, so it has to be positive. Here you input from the negative, or you counter the negative first. So this one has to be negative. That's exactly what I did. So I took here, this one here is a positive, this one is a positive, and this one is negative. Okay, and then you have only one unknown in this equation, you can get Vx. Okay. Let's have another example here, very straightforward, very easy. So here I have a current this way, 2 milliampere. I have current this way, Ix. Okay. I have current this way. This is a dependent current source. And the value of the current here is 2Ix. And Ix is the current here. Okay. So the current is this way. And then I have current here for 4 milliampere. Okay. What I need to know here is this current. So very, very simple. This very direct application, very easy application for Kirchhoff current law. This is one node, this is input. This is another one input, so 2 input and 2 output. That's what I did. So the input here, this one and this one, equal to the 2 outputs here. Okay. You have only one unknown, I can calculate it. Any questions? Okay, so I'm going to leave this one to next time. Okay, I have another example here. You can start with the quiz.